Hello, it is Advent of Code day, well, it's day 20, but we're going to do day 12. I've been in the process of moving between jobs, going from one to the other, and that means that, you know, it's been a bit hectic. I'm also noticing my mic's peaking a bit, so I'm just gonna crank the gain down just a little bit. Hopefully that should be a more comfortable gain, and I should peak a bit less. So, day 12. I'm going to read this, and I don't need to read this because that is pathfinding algorithms. So this is going to be our connections, this is a visual representation, this is the paths from start to end. What's the quirk? Lowercase letters. We cannot visit lowercase letters more than once. We also can't visit start more than once. Because otherwise, like, start A, start B, end would be in this list, which it isn't. So that... Okay, we can definitely make that work. So let's go, and I've already scaffolded this, as you can see. Let's go and open 2021 day 12. And let's start by filling in our test and passing our input. Now, I think we have a few test cases in here, right? We have 3 test cases. So here's our first task. Here's our first one. I'm going to just call these P1 is equal to this. Then T2 is equal to this, and then T3 is equal to this. Need to get the hash after that. Okay, and we care about the number of different paths there are. First one, it is 10. Let's do assert task pass task 1 T1 10. Then T2 has 19. T3 has 226. 226. So that should be our tasks. Okay, so there's a couple decisions to make when you have an Advent of Code pathfinding puzzle. The first and most important is how we represent those, and I think here what we're going to want to do is we're going to just want to have an adjacency list. But for we're actually going to want 2 structures. We're going to need our past input, which is just the connections, and then we're actually going to have our network. Our cave map is caves. These are caves. Subterraneans. Caves. Okay, we have our cave map, and our cave map is going to have a connections, and the connections is going to be a hash map from. You know what? We can use a B tree map. A B tree map from character to a vec of character. And then our past input is going to be from. So we'll have a struct connection from. You know what? Rather than from 2, we'll call them left and right. And you'll see why I'm using character in a minute. What we can do is. All of these are single characters, right? In our big puzzle input, we're all single characters. We're strings of characters. That's the kind of thing that would have been good to know. I guess they have some in here. Yeah, okay, I see that. In that case, let's say that we are strings. We can just propagate a lifetime through here. And we are maps from this. Then in that case, we'll do a hash map. from string to string. And all of these are just going to be referencing things in go. And tick A will be the lifetime of our input here. And so that will automatically get bound to the lifetime of our output here. And then in here we can say connections is equal to config of connection of tick A. Okay. And hashmap has a capital N. Nice, okay, so now let's write our parser. We're going to need, I'm looking at these, we're going to need we're going to need character complete alpha1. We're going to need byte, we're going to need char as well to match our single hyphens. We're going to need combinator value and combinator map. We're also going to need line ending, and we're going to need multi-separated list. Okay, and so now what we can do is we can say let connection is equal to map from alpha1 oh, and we also need to bring in parser alpha1 dot and map and a hyphen and alpha1. We want to map that. You know, let's rather than using and, let's use separated pair here. Separated pair just feels a bit nicer. Sequence separated pair. So here what we're looking for is a separated pair where we have got alpha1, a character of a hyphen, and then alpha1 again. So that should map grab a connection, and then we want to map that from left right into connection left right. Then for our connections, we have a separated list one of line ending and connection. And then for our parser, we have connections going into parsed input of connections. And parser.parse on input. Okay, so that should give us a good let's do some derived debugs here. And then let's have a look. We got start to A, start to B. That looks correct to me. B to end. Yup. That looks completely correct to me as a parsing of our input. Okay, so now we have a parsed input. We're going to need to implement cave map. We'll give it a function from connections. You know what? Let's implement from iterator for cave map. What's missing from here? Anti-case. We need to say what the type of the iterator is. Yeah, okay. And then all we need to do here is we need to say for connection in connections. For iter dot map from an. So each of these is going to be a connection. And what we want to look at is the so what we can do is we can actually fold this. Oh wait, no, we can flat map it. And what we can do is we can say, oh no, you know what? We can fold. Fold is the better operation here. So we want to bring in a hash map new. And then in here we want to say map dot entry left or insert vec new, which should be or insert with vec new dot push right. And then the same where we backlink the right to the left. And then finally, this is a mutable map. We return our map at the end of the fold. And then in here we say this is a cave map with connections as defined by all of that. It doesn't like something. What doesn't it like? It doesn't like that we've not opened a scope here. What don't you like? Method fold exists. Let's have a look in the cargo check. Oh, of course. There we go. Expected Anstra. Yeah, this should not be Anstra. This should be item is equal to connection tick A, and then this here should be connection tick A. Cool. Okay, so now we have a way of building a cave map from an iterator of connections, which we're going to do in here. Now we actually have an iterator to references to connections, which is actually fine here. So let's do that instead. Let's say we have some reference tick B such that tick B will die before tick A dies to and tick B connection of tick A. Okay, and now what we should be able to do is we should be able to say let cave map equal cave map. Yeah, just say input dot input connections iter collect. And we should be able to collect into a cave map. Nice. Okay, so now we have our map. What do we need to do with our map? We need to traverse our map, which means we're going to need a recursive sort of seeker. The recursive seeker is going to have to visit. We can depth first through. I think the graphs will always be structured such that shouldn't cause any problems, and we just if our candidate for traversal is lowercase or start, then we do not traverse there, and if it's end, we increment our count. So what we'll do is we will have a count paths method that takes in our map. We really don't care what type of cave, what the lifetime on the cave map is. It takes in a position, which is where we currently are in the map. It takes in a visited, which is going to be a hash set of Anstra. And I wonder if we can just elide the lifetime, or if Rust will shout at us. So we have an and string of the places we visited, and we have a total parts found of usize, and technically, sorry, of an and new usize. Okay, and so in here, what we want to do is we want to say let mute count is equal to 0, and then let mute visited. Well, visited is only matters as we descend a path, so we could actually don't need to. We can pass it in as an initial. Visited is hash set new. And then what we'll do is we'll say count paths in our map for start. It's lowercase start. It's lowercase start. Start being lowercase is actually really convenient. It means we can just check that the whole string is lowercase. We have visited our. Let's just say hash set new here. And we have found 0 paths. So that will form our. We'll just say we'll need reference count that, and then here we will return the count and we will return a usize. Okay, so that should all work. Yep, we just need to make it actually solve everything in here. So from our current position, so what determines if we are over? If we are over, if position is equal to end, then paths found increments by 1, and we terminate the branch because we found an end. So that is our base case for the recursion, nice and easy. Now our traversal case, what we need to do is we need to say let candidates is equal to, and you know what? Let's say that our map here is only a read map. I don't think we will ever. We don't need to ever mutate it, so that is fine to just be a read map. Okay. Expected. We need to update this to say usize. Okay, so we say our candidates are equal to our map dot connections dot get at position. Unwrap all default. So that's going to get us our candidates. And then what we need to say is for candidates in candidates, if candidate.cars, there's no is lowercase, is there? If candidate.cars.all cc.is lowercase, is ASCII lowercase, even nicer. If they are all lowercase, then we say if visited.contains candidate, and then we continue. Otherwise, we're fine. So we can actually combine those, but for now, that's not. And then otherwise, what we need to do is we need to recurse, and we need to say count paths. Map is still map. Position is now candidate. Visited is now. So here we actually need to do then here is at the start here we say. And you know what? Visited can be a. Visited is fine to just be owned. We're going to clone it everywhere. So we'll say let visited. We'll take it by mute. It's going to get cloned when we pass it in. Let visited equal visited insert position. Should be fine. And then in here, what we need to do is we need to say candidate. We pass in visited.clone. And we pass in paths found as is. All right. We'll just say if let some candidates is equal to all of this. Otherwise, there's no candidates to care about, which I don't think should ever happen, but you know, it might be nice to know. Let's just say that everything is using the same lifetime, because our position is going to be at least this lifetime, so that should now be fine. There we go. We're just specifying that these are all you know, the same constraint applies to each of these. In fact, I think maybe what's the minimum restriction we need? All we need to do is mark that those two are the same. So that's position, and so yeah. So as long as this and this have equivalent lifetime, then it should be, the type check should be happy. How does it feel about our test? Doesn't like it. Interesting. Curious. Trace where you are as we explore. We go from start to A. Oh, no, yeah, continue here means go on to the next iteration of the candidate loop. So move to the next candidate. Let's maybe look at our graph. Maybe the graph is the issue. If I say in here debug map dot connections with an ampersand before it. Aha! Found the connection. Problem, we only have a single connection from start to A. What is wrong with this then? So the left links to the right links to the left, and we go on to the next one. Did I break our... Did I break our parser somewhere along the way? Yep. Oh. Somewhere along the way our cargo format decided to do that. That is very... Oh, you know why? It's because I did like a big equals pass at some point, and equals doesn't respect you. That's annoying. Okay, well at least I spotted it. This could have been the kind of thing I took forever to figure out. Now do my tests pass? Now I get way too much output. Nice, test passed. Okay, cool. So that's part one done. Nice and easy. Okay. So let's actually have a look at the output for that. And it is 3369, which is the correct answer. Okay, part two. After reviewing the available paths, you realize that you might have time to visit a single small cave twice. Specifically, big caves can be visited any number of times. A single small cave can be visited at most twice. The remaining small caves can be visited at most once. However, the cave's name, start and end can only be visited exactly once each. You leave the start cave, you may not return to it, and once you reach the end cave, the path must end immediately. Okay. Okay, so we have some test cases. So let's go and fill those in. So down here. So for task 2 part 1 there is now 36. For task 2 part 2 there is 103. And for task 2 part 3 there is 3509. Okay. And so for task 2 all we need to do is modify our count. Let me think. So what we can do here is we can actually rework these conditions a little bit. What we can do is we can say if they are all lowercase, and visited contains candidate. I'm just cleaning up part 1 a little bit. So that should work the exact same for part 1. We fail on part 2. Yeah. So we failed on this 36 here. So now with that, what we can do is we can, and you'll see why I'm modifying this, we can say a maximum small, we can say a, so you can visit a single one twice. Okay. I think for clarity, let's just make a count paths 2. And then let's just like implement it slightly differently, but only slightly, and just like modify this like this. Okay, so count paths 2 has the major difference that if the candidate.cars, if it's entirely lowercase and visited contains candidate, and we have a flag here which is that double visit is false. Double visit is a boolean, and double visit here is false. Yeah, so let's actually match candidate. So we've got, if our candidate is start, then we continue. We never return to start. If it's end, we've ended immediately, so we don't need to account for that here. If it is if c.cars.all c.is ASCII lowercase and not double visit and visited.contains. Okay, hold on. If it is all lowercase and not visited.contains candidate, then what we do is we say, so our visitor will get added to our candidate the second we visit that. So yeah, if it is if and visitor contains candidate and not double visit. Let's actually do the double visit check inside this branch. So if it is if C is lowercase and we already have it, then we say if double visit continue, else double visit is true and so here we are still false. Oh no, here we stay as we are, so we say double visit. That's that one there. Here we say count paths 2 map candidate visited.clone true paths found. And then finally, for all other cases, we'll say, we'll call this candidate. And here we'll say candidate. Nice, test passed. So yeah, what we do is say if it's start, continue. We never go back to start. If it's all lowercase and we visited before, if we've already double visited, then continue. Otherwise, count the paths, but now we have double visited. And then for any other candidate, just count the paths and persist our double visit. So that should be that nicely done. So let's go have a look at our result. 85883. 85883 is the right answer, and that is Advent of Code Day 11 done.